Now, in the first session of our training package, we're going to talk about what is CFD, or Computational Fluid Dynamics. For the second part, we're going to talk about the examples and applications of CFD in industry or academia. And for the next part, we're going to talk about and explain some theories and formulas that are used behind mechanical engineering problems related to fluid flow or heat transfer. For the next part, we're going to talk about the most renowned algorithm for solving fluid flow problems numerically, which would be the simple algorithm. And for the final part of this session, we're going to build our first project from scratch, meaning that we're going to build the geometry. After that, we're going to mesh that geometry. And after that, we're going to set up the Fluent software settings for this project. Now, to talk about computational fluid dynamics, or CFD, as most of you guys probably would know, computational fluid dynamics is the science of predicting the fluid flow, heat and mass transfer, chemical reactions, and related phenomena by numerically solving the set of governing mathematical equations. As we all know, there are three approaches to solve problems related to engineering or fundamental sciences like physics, chemistry, etc. The first solution would be the theoretical solution. Now, in this solution, you need to oversimplify lots of equations in order to solve your problem, or you have to have a strong mathematical background. The second solution is the experimental solution. Now, this solution is very time consuming, very expensive, and probably the most important point about this solution is that it is not applicable to all problems. So what do we have left? The numerical solution. Now, the condition for this solution is a little different from the two former solutions. Now, in this type of solution, if you have good CFD knowledge, you would be able to simulate almost all of the problems related to engineering or fundamental science without having the shortcomings of two former solutions. Assume that you're a car maker and you've designed a new car. Now you want to test your car in order to calculate parameters like drag force applied on it, or the down force applied to the car by its front and rear spoilers. Now, one solution would be to build this car, put it in a wind tunnel, and calculate those parameters, which would be extremely expensive. Now, what would be the solution then? The solution is to simulate the airflow around this car by CFD analysis and CFD software. Now, the same explanation is applicable here as well. In order to analyze aerodynamics of this airplane experimentally, you should have a wind tunnel that this airplane fits in. However, some of you guys may think that we can use a smaller model of this airplane or this car and put it in the wind tunnel. In that regard, it should be pointed out that in front of the experimental work, there are numerous challenges. For example, the challenges of how and where to put the props on the surface of our airplane or car. Or the next challenge would be whether the operator is skilled enough in order to read the data correctly. Now, turbomachinery simulations are very interesting. By comparing two solutions of numerical and experimental solutions, numerical solutions have a great advantage in this part. For example, an experimentalist wouldn't be able to calculate the pressure changes on one of the blades of these turbomachines. But you, as a CFD engineer, you would be able to calculate all different parameters inside the rotating zone. And another interesting simulation that we can do using Fluent software is a simulation of horizontal axis wind turbine that we will simulate and explain the settings for it in forthcoming sessions. And as we progress in our training sessions, in one session we will explain how to set up the settings for Fluent softwares in order to simulate a shell and tube heat exchanger. And of course, another application, another simulation that you could do is the simulation of multi-phase flows. Now, in this slide, you can see the fundamental equations that are used for fluid flow and heat transfer problems. The first term on the left side of the equation is called the unsteady term and calculates the changes in parameters that are placed inside the parentheses based on time. Now, if we put aside this term, the term that is left on the left side of the equation is called the convection term that is related to the fluid flow velocity. The first term on the right side of the equation is related to the pressure of the fluid film. And after that, we face the term which is called the diffusion term, which is related to the viscosity of the fluid. And for the final term, you can see that this term is designated by S and represents the source terms. Now this source term can be replaced by different forces based on your project. And for the energy equation, we're going to explain this equation in next session where we simulate the heat transfer inside a heat exchanger. As you all probably know, the Fluent software is a software that uses the finite volume method to solve problems related to fluid flow and heat transfer. Now, the most renowned algorithm for solving these problems numerically is called the simple algorithm. On the right side of this slide, you can see the flow chart related to this algorithm. In the first step of this algorithm, we get a guess and initializing values for pressure and velocity field. In the next step, the software will calculate a secondary values for the velocity field using the momentum equation. And by using those secondary values of the velocity field, the software will calculate a secondary value for the pressure. After that, the software will correct the values of pressure and velocity field using the secondary values for each of them respectively. Finally, this loop is repeated until the results are converged. Now, for those of you who are interested to know more about the finite volume method or the equation discretization methods, or even know about different algorithms that are used to solve the problems numerically, we recommend you to read the book called Numerical Heat Transfer and Fluid Flow by Patankar. You can also use the link shown in this slide to download the PDF. As our first project, we will investigate the Poiseuille Flow, and we will solve this problem using theoretical solution and Navier-Stokes equation. Now, if you've followed our theoretical solution, and as you probably knew, the most important result that we can elicit from this solution is that the maximum value for our velocity happens in the middle section of the channel, and its value is equal to 1.5 times the average velocity. Now, using numerical solution and using Fluent software, we are going to extract the same result that is shown here. Now, in order to build our project, we will find and select the fluid flow block and then drag it in the blank space in the workbench software. The first stage is to design the geometry. To do that, we right-click on the geometry part and then select New Design Modular Geometry. In the Design Modular software, the first step is to change the units. Therefore, we click on Units button and select millimeters. Our next task would be to select our main plane in order to sketch our geometry in it. To do that, for example, we select XY plane and we click on New Sketch button. Now, after clicking on the New Sketch button, under the XY plane, you will see that a sketch is generated. Now, in order to see this sketch perpendicularly, you just have to click this button. Now, in order to sketch our geometry, which is a rectangle, we click on Sketch 1 and then underneath it we click on the Sketching button. Now, as was mentioned in previous slide, as our geometry is a rectangle, we click on Rectangle Geometry and draw this geometry in the blank space. Now, after drawing the geometry, in order to give dimensions to it, we click on Dimensions button and we select Length. Now, after selecting this dimension type, we click on vertices of our rectangle so that we can give dimensions to that edge. We also want our geometry to be built in a symmetrical form around the x-axis. Therefore, we select one vertex as our first point, as you can see in this slide, and as for the second point, we select the x-coordinate. Now after fully concentrating our geometry, on the lower left side of the software window under the dimensions section, you can see that 3 dimensions are available, and we will set each of those dimensions as follows. Now that we drew the outline of our geometry, we need to turn this sketch into a surface. To do that, we click on Concept and then select Surface from Sketches. Now after we click on that button, under the Tree Outline section, we select our sketch and then click on Apply on the lower left side of the software window. It should also be pointed out that in front of the Operations section, we change the Add Material format to Add Frozen. Now in the projects where you have multiple geometries, if you select the Add Material operation method, the software will assign different materials to those geometries and somehow do not count them as a whole and complete body, but different geometries. But if you select Add Frozen, the software will count those geometries as one body. However, in this project, since we only have one body, there wouldn't be any difference between Add Material or Add Frozen. Now after defining the settings, we click on Generate button and the software will turn this sketch into a surface for us. There is also one other point worth mentioning, which is that if you expand the Part section, you can see that one surface body exists here. Now on the lower left side of the software window in front of the Fluid or Solid section, we need to change it from solid to fluid, since we are going to have fluid flow passing inside this, or in other words, this geometry would be our computational domain in which the fluid flows. At this point, our work with the Design software is finished. Now we save our geometry and then we close this software. After we created the geometry, it's time to generate mesh for it. To do that, we double click on the mesh button. In the ANSYS meshing software, under the Outline section, you can see different parts. For example, if you click on the geometry, you can see the surface body that we had created in the ANSYS Design software. Or if you click on the coordinate system, you can see the coordinate system where we had used in Design software in order to create our geometry. Now we reach to the mesh part, which is the most important part in this section. Now if you click on mesh on the lower left side of the software window, you can see different settings for this part. Now these settings will be investigated step by step in our different projects. Now if you right click on mesh, you can see 2 different buttons are available here, update and generate mesh. Now in order to understand the difference between these two, consider that you have applied your desired settings and methods to your geometry in order to mesh it. If you change the number of mesh cells on one edge, for example, and then click on Update button, the software will automatically change the mesh on that edge only. But if you click on Generate Mesh button, the software will start to mesh your geometry from the beginning, no matter if you've only changed the one edge setting. Now, as our first task in meshing the geometry, we want to give sizing or assign number of divisions or number of mesh cells on an edge. To do that, we right click on mesh and then go over insert and select sizing. Now the next step is to select the desired edges, which are the left and right edge of the geometry. After selecting the two edges, we go over the geometry and click on the apply button. After that, under the definition section in front of the type, we select number of divisions since we want to assign the number of mesh cells over these edges. Now in front of the number of division, we enter the value of, for example, 30, and the software will divide these edges into 30 divisions for us. Now in front of behavior, there are two options available: soft behavior and hard behavior. Now if we select the soft behavior, there's a slight chance the software will change the size of the division sections when we add other settings or other edge sizing for different edges. Therefore, we almost always tend to select hard behavior. Now after defining the number of divisions over these two edges, it's time to add the boundary layer mesh manually. To do that, we click on BIOS and we select the mesh type that has bigger mesh cells in the middle section and has smaller cells on their sides. After that, in front of the bias factor section, we enter the value of, for example, 3, meaning that the biggest cell, which is placed in the middle section, has a width 3 times bigger than the smallest cell. Now, if you zoom a little bit over one edge that you have assigned mesh settings for it, you can see the number of divisions that is applied on this edge, and you can also see the effect of bias type and bias factor where we had selected in previous slide. And of course, you can easily observe that the mesh cells that are placed on the corner of this edge are smaller than the mesh cell that is placed in the middle section, and the width of that biggest cell is 3 times bigger than the width of the smallest cell that is placed in the corner of this edge. Now, in order to assign number of mesh cells or number of divisions to the upper and lower edge of the geometry, we do the same thing that we did for two previous edges, and we right click on mesh and then go over insert and select sizing. Again, after clicking and selecting the two edges at the same time, we go over geometry and we click on apply button. After that, just like the previous edge setup, we click on the type and we set it to the number of divisions. Now here we set the number of division to 1000 and we set the behavior to hard. Now after defining a number of mesh cells over the outline of our geometry, we need to make the software to understand that we want a complete quad mesh over the surface of our geometry. To do that, we right click on mesh again and again go over insert and select face meshing this time. After selecting the face meshing option, we click on the surface of our geometry, and then on the lower side of the software window in front of the geometry, we click on apply. After applying in front of the geometry, you need to make sure that in front of the mapped mesh section, we have selected yes, and in front of the method, we have selected quadrilateral since we want the surface of our geometry to have a square-like meshes. Now after defining all the desired settings, we click on Mesh and we select Generate. After zooming a little bit over the surface of our geometry, you can see that boundary layer mesh along with mapped mesh is generated over the surface of our geometry. Now after the mesh was generated, if you click on the statistics button and expand it, you can see the number of mesh cells for your geometry, which in this project is equal to 30,000. Now for those of you who are interested to know about the mesh quality and the parameters related to it like aspect ratio or skewness, you just have to expand the quality and then in front of the mesh metric, select your desired parameter. Now aspect ratio for one cell is considered as the ratio of the size of the biggest edge of that cell to the smallest. And for having the highest quality mesh, we need to make sure that this parameter is as near to 1 as possible. But this doesn't mean that if we have an aspect ratio higher than 1, we can't solve our problem inside that mesh. Skewness is a parameter which accounts for the changes of mesh cell shape, comparing it to a perfect square, which should preferably have a value near to 0 as possible. Now it is time to set names for our boundaries in order to have an easier job in the Fluent software where we want to adjust the settings for them. To do that, we right click on our desired edge and then click on Create Named Selection. Now in the appeared window, we set the name of this boundary to be Inlet Boundary. Here we select the upper wall and right click on it and then select Create Named Selection. We follow the same step for the lower wall. And finally we select our right edge of the geometry and right click on it and then click on Create Named Selection, and we set the name of this boundary to be the Outlet Boundary. Now if you expand the name selection part, you can see that we have defined 4 different boundaries over our 4 edges. But there is still one thing left, and that is we should give name to the surface of our geometry where the fluid passed. To do that, we click on Face Selecting button and then select the face of our geometry. After selecting that face, we right click on it and then click on Create Name Selection, and we set the name of this part to be Flow. After assigning the name to the surface of our geometry, the work in the meshing software is done, so we close this software. Now after double clicking on the setup, the Fluent Launcher window will appear. In the appeared window, under the Options section, we enable the double precision. When we enable this option, we make the Fluent software to calculate the values of different parameters with 16-digit precision after the point. Also, you can see that Display Mesh after reading option is automatically selected.
Now under the parallel section in front of the solver processes, you can enter the number of CPU cores you want to use to solve your problem. For example, in this system, I have maximum of 4 CPU cores, so I enter the value of 4. After selecting your desired option, by clicking on the Start button, the Fluent software will start. In the Fluent software, there are multiple ribbon tabs from Domain to Design, where you can use them to apply different settings. For example, in order to add a user-defined function, all you have to do is to click on user-defined and then go over function and add your UDF. However, in this project, we only get to work with the outline, task page, and graphics and console section, and the previous stuff will be explained on the right time.
Under the General Setup tab, you can see different buttons from scales to units. By clicking on the scale,
In the appeared window under the domain extent, you can see the extents of your geometry or dimensions of your geometry. Also, in the view length unit, you can see that meter was selected, showing you that the values that exist in the domain extents are in the meters unit. Also, if you click on mesh was created in section, you can see different units from millimeter to other units, which gives you a scaling factor. Now, if you select, for example, centimeters under the scaling factor, you can see that the factors of 0.01 will be shown. Now, if you click on the scale button, under the domain extents, you can see that these values will be multiplied by the scaling factor. And if you click on the unscale button, everything will be back into its previous state. Now, this option will be used when you have designed your geometry, for example, in the meter unit, and you want to change it into, for example, millimeters. You just click on millimeter and then click on scale, and your dimensions will change from meter to millimeter.
by clicking on Check button, you will see that under the Console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on Report Quality, again in the Console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on Display button, a new window will appear, which you can see different parts of your geometry.
This window under the options, if you enable the faces, you can see the faces of your geometry, and if you click on edges, you can see the mesh cells of your geometry. Now if you click on the units, a new window will appear showing you different parameters and quantities in the Fluent software. If you click on any of these quantities, a list of units that are available in the Fluent software will be shown. For example, if you select the velocity under the unit section, you can see different units from meter per second to centimeter per second. Consider you have a problem where you want to use British units instead of SI units. You just can simply change the meter per second unit into foot per second. Now under the solver section, you can see different parts are available. Under the type section, you can see two options are shown here, pressure-based and density-based. Now we use pressure-based solver when we are dealing with incompressible flows. And we use density-based solver when we are dealing with high Mach number flows or compressible flows. As for the velocity formulation, two options of absolute and relative are shown. As you can guess by their name, we select the absolute format since we want to enter the absolute values for the velocity. And for the time study, you can see steady and transient time study are available. A steady time study refers to a study where we don't calculate the effect of time in our simulation, And of course, transient time study is selected when we want to calculate the effect of time. And of course, since we have a two-dimensional geometry in our project here, you can see that the planar 2D space is selected. The other two options will be explained in next project. Also, you can enable the gravity in the Fluent software just by clicking on gravity and entering the value of gravity in any direction that you desire. Now, if you expand the model section, you can see different models from multi-phase, energy, viscous, radiation, and so on. For example, if you want to enter the energy equation and calculate the temperature changes inside your computational domain, all you have to do is to double-click on energy model and enable this equation. But since we only want to analyze the fluid flow in this problem, we do not enable the energy equation and cancel this window. Instead, we double-click on the viscous model, and in the appeared window we select the laminar model, since the fluid flow entering our computational domain does not have a high velocity and therefore does not have a high Reynolds number. Now, after defining the desired model, it's time to select a material for our fluid. To add a new material, all you have to do is to right-click on Fluid and then select New. In your window, you either can add a new material by defining its properties yourself, or you can just simply click on Fluent Database and select your desired material from the list of available materials in the Fluent software. Now, after clicking on Fluent Database button in the appeared window, we search for water liquid material to add it to the software. Now, after adding the water liquid material under the properties section, we only change the values of density and viscosity slightly so that it would be easier for us to calculate the Reynolds number. Now, after adding the desired material, all you have to do is to assign this material to the appropriate zone. To do that, we expand the cell zone condition and double click on the flow. In the appeared window in front of the material name section, we change this material from air to water liquid. Also, if you click on the edit button in front of it, you can see the properties of the selected material. Now it's time to set the boundary condition. To do that, we double click on the boundary conditions button. Now, if you click on the inlet boundary, you can see that the type of this boundary is defined to be velocity inlet. You also can change this type into, for example, mass flow inlet by just clicking on the type button. However, we left this setting unchanged and we click on edit button in order to change the settings for this boundary. In the appeared window in front of the velocity magnitude section, we enter the value of 0.025 meter per second so that it would give us the Reynolds number equal to 1000. Now, if you select the interior flow boundary and click on edit, in the appeared window you can see that there is no setting that need to be changed. Now, if you click on the outlet boundary, you can see that the type of this boundary is defined to be pressure outlet. Just like the previous boundary, by clicking on edit, a new window will appear in which you can change the settings for this boundary. In the appeared window in front of the gauge pressure, you can see that the value of 0 Pascal is defined. Now, as you all probably know the correlation between total gauge and atmospheric pressure, when we set the value of gauge pressure to be equal to 0, we mean that the total pressure on the outlet boundary is equal to atmospheric pressure, meaning that our fluid flow will exit this boundary to the atmosphere. Now, as we mentioned the atmospheric pressure in previous slide, if you click on operating conditions, under the operating pressure, you can see the value of atmospheric pressure. Now, if you click on this wall boundary, under the momentum tab, you can see that stationary wall motion along with no slip shear condition are defined for this wall. Now, if you click on this wall boundary, under the momentum tab, you can see that stationary wall motion along with no slip shear condition are defined for this wall. After defining the settings for boundary condition, we left the other options and buttons unchanged and we double click on the methods.
After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order advent and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under relaxation factors for different parameters. Now these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the zero, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence.
Now, as was mentioned in theory section about numerically solving a fluid problem, we need to make a guess for the initializing values for the needed parameters to solve the problem. Now, if you double click on the initialization button, in the appeared window, there are two options available, hybrid and standard. In the hybrid method, the software will automatically solve a Laplace equation in the domain and calculates those initial values by itself. However, in the standard initialization method, the user or the operator gets to choose these initializing values.
Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software.
Now after initializing the solution, the final step is to double click on the run calculations and set the number of iterations you want your simulation to progress and continue. After that, by clicking on calculate button, the simulation process will start.
After the simulation progress is done, it's time to extract the resulting contours. To extract different contours, we expand the graphics section and right-click on Contours button and click on New.
In the appeared window under the contour name, as its name is obvious, you can change the name of this contour. Now under the options section, the first three options have to be enabled all the time. About the global and over range, if we enable these two options, we would be able to determine the maximum or minimum values of our desired variable by ourselves. Now this option might come in handy when we want to see the ranges of changes in, for example, velocity variable in special places of our geometry.
Now under the coloring section, you can see two options of banded and smooth are available here. Now the difference between these two options will be shown visually when we extract the contour.
Now in order to extract the contour, under the contours of section, we select our desired variable, which in this slide we are going to select pressure. After that, under the surfaces section, we select the flow and click on save or display button. Now about the banded and the smooth option. If you select the banded option and then click on save or display button, you can see that the color in the contour will become separated. Now in order to extract the contours related to the velocity, we just have to click on contour section and select the velocity variable. After that, just by clicking on save or display button, the software will show us the velocity contour. Now as you can see in this contour, the colors are separated from each other. If you select a smooth coloring option and then click on save or display button, you will see that this color separation will be gone. And of course, if you zoom a little bit near the inlet boundary, you can see that the boundary layer starts to form. Also, in order to extract velocity vectors, just have to right click on vectors button and then select new. Now in the appeared window under the surfaces section, all you have to do is to select the flow and click on save or display button. Now if you increase the value under the skip, as its name is obvious, the software will skip and delete some of these vectors. And if you increase or decrease the value under the scale, you can change the size of each vector. Now in order to extract more detailed results, we need to define a horizontal line in the middle section of our surface. To do that, we right click on the surfaces and then go over new and select line or rake. In the appeared window under the endpoint section, only by entering the first and ending point of your line, the Fluent software will draw this line for you. After entering the values for first and end point of the line, as you can see in this window, we click on Create button. Now in order to see the created line, all you have to do is to expand the graphics and then double click on the mesh button. In the appeared window, you just have to select and click on line number 6 and then click on Save or Display button. Now as you can see, the line that we wanted to be placed in the middle section of our geometry is generated. Now there is still one line left which should be vertical and be placed near the outlet boundary since we want to extract the velocity profile shape. To create the second line, just like the previous slide, we right click on surfaces and then go over new and select line or rake. In the appeared window, you should enter the values for first and ending point as you can see in this window and then click on create button. Now just like the previous line, we again double click on the mesh button and in the appeared window, we click on line number 7 and click on Save or Display button so that we can witness and see both lines together. Now after creating the lines where we want to extract the shape of profiles on them, we expand the plots and double click on XY plot. In the appeared window under the plot direction, we need to determine the direction of our plot. For example, we want to extract the changes in pressure or velocity in X direction. So we need to set the value of X to 1 here. Now in order to extract the changes in pressure along the horizontal line that we had created in previous slide, all you have to do is to set the y-axis function to pressure and then under the surfaces select your line number 6. After that, by clicking on Save or Plot button, the software will show you this plot. Now in the plotted diagram, you can see that at the inlet boundary, the fluid has a pressure of 0.6 Pascal and this pressure reaches 0 when the fluid reaches the outlet boundary. Now in order to extract, for example, velocity changes along this horizontal line, you just have to change the y-axis function from pressure to velocity. And in this plotted diagram, you can see that the velocity nears and reaches a constant value at the final section of our geometry. Now in order to extract the shape of the velocity profile, you just have to change the plot direction and we set the value of y to 1 since we want to calculate the velocity changes in y direction. After changing the plot direction, we set the y-axis function to velocity and under the surfaces section we select line number 7 which is placed at the end of our geometry section. And now in this plotted diagram, you can easily see the shape of velocity profile. Now as you can see in this plotted diagram, the velocity values are separated from each other. In order to make it a complete line, all you have to do is to click on curves and then change the pattern of the diagram. Now in order to extract the data related to these diagrams, all you have to do is to enable the write to file option. After that, by clicking on write, you will be able to save a file where you can see and use the data inside that file by using Notepad or Excel software. Now, in order to calculate the exact value of velocity at the outlet boundary for comparing it to the theoretical value, we expand the report section and we double-click on surface integrals. Now, in the appeared window under the report type, we select facet maximum in order to calculate the maximum value of velocity at the outlet boundary. After that, under the field variable section, we select the velocity variable, and under the surfaces section, we select the outlet boundary. After that, by clicking on Compute button, the software will give us the maximum value of the velocity. Now, if you compare these two values, which are resulted from numerical solution and theoretical solution, you can see that almost 10% error exists between these two values. Now, the main reason behind this error is due to the short length of our geometry, meaning that our fluid flow didn't reach the fully developed state.
To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.